Let us start chapter 5 module 11. In this module, let us first consider an example that whether R2 can be covered by countably infinitely many lines. The answer is no. But why? The answer is that R2 is a complete metric space and every line in a complete metric space is of nowhere dense. That means the interior of its closure is empty, and we know that no complete metric space can be expressed as countable union of nowhere dense set. This is the reason that R2 cannot be covered by countable union of lines. In this module, we shall discuss about those topological spaces which has such kind of properties. The topological spaces which has this type of properties will be called bare spaces. We shall see that every compact topological space will be bare spaces, every complete metric space will be bare spaces. We shall also see that locally compact Hausdorff spaces will also be bare spaces. Let us go to slide presentation. So, in the introductory discussion, we have given the idea of bare spaces. Next, we are going to formally define the bare spaces. A topological space X is said to be bare spaces if given any countable collection of closed sets, each of which has empty interior, their union has also empty interior in capital X. By this definition, it can be easily verified that capital R is a bare spaces. We shall also prove a theorem from which it will follow that capital R is bare spaces. But this definition of bare space is given in terms of closed sets. In the next proposition, we shall give a definition in terms of open sets. So, we are going to give an open set formulation of bare space. Lemma: a space X is bare space if given any countable collection UN of open sets, each dense in capital X, their intersection is also dense in capital X. To prove this lemma, it is sufficient to show that a set capital A in a space X has empty interior if and only if its complement is dense in that space. As I have claimed in the introductory discussion, let us first prove the following theorem, which is also called bare category theorem. If capital X is a compact Hausdorff space, then capital X is a bare space. To prove this theorem, we shall use the closed set formulation of bare space. So, let AN be a countable collection of closed sets having empty interior. That means no open set is contained in any of an. Our claim is that union of an has also empty interior in capital X. So, to prove this, we have to show that union of an does not contain any open set. For this, let us consider an open set U naught of capital X. We have to show that U naught is contained in union of an. That means we have to find a point X in U naught that does not belong to in any of the sets an. Let us first consider the set A1. By given hypothesis, A1 does not contain a U naught as capital A1 has empty interior. Therefore, we can choose some point y in U naught which does not belong to A1. Now, A1 being closed, there exists some open set containing y which misses A1. But we know that capital X is compact Hausdorff and therefore normal and hence regular. So, by regularity criteria, we can find an open set U1 whose closure is contained in the open set considered here. That means we can choose a neighborhood U1 of y such that closure of U1 intersection A1 is empty set and closure of U1 is contained in U naught. In this way, we can choose an open set again U2. Now, let us consider that we have choose U1, U2, Un minus 1 where y belongs to Un minus 1, that is not contained in the closed set An, and now we like to choose an open set Un to be a neighborhood of this point such that closure of Un intersection An is empty and closure of Un is contained in Un minus 1, which we can do by mathematical induction. Now, since capital X is compact, then intersection of Un is non-empty as the collection closure of Un has finite intersection property. Now, to complete the proof, if X is a point of intersection of Un, then X is in U naught also, because closure of U1 is contained in U naught, and as for each n, X does not belong to An because closure of Un is disjoint from An. This completes the proof of this theorem. Next, we shall prove that complete metric spaces are also Baire spaces, as I have claimed in the introductory discussions. But to prove this, we require the following well-known lemma: let K1 contains K2 be a nested sequence of closed sets in a complete metric space, then if diameter of Kn tends to 0, then intersection of Kn is non-empty. To prove this, let us choose xn in Kn for each n. Now, because xn is in Kn for all n greater than capital N, and as diameter of Kn tends to 0 as n tending to infinity, one can make the sequence xn so that xm and xn are very close as mn tends to infinity. That means the sequence xn is a quasi sequence. Suppose that it converges to x, then for given L, the subsequence xl, xl plus 1 also converges to x. Thus, x necessarily belongs to closure of KL, which is equal to KL, as KL is a closed set. Therefore, x belongs to intersection of Kn. Now, we shall prove that complete metrizable space is Baire space. To prove this, let us consider An be a countable collection of closed sets of X which has empty interiors. We claim that union of An also has empty interior. For this, let U naught be an open set of capital X. We can proceed as the previous theorem. Let us first consider the set capital A1. Since A1 has empty interior, it does not contain U naught entirely. Therefore, we can choose some y in U naught that is not in A1. We choose a neighborhood U1 of y with diameter U1 less than 1 such that U1 closure intersection A1 is empty and U1 closure is contained in U naught. In general, given the non-empty open set Un minus 1, we choose a point y in Un minus 1 that is not in the closed set An, and then we can choose Un to be a neighborhood of this point such that Un closure intersection An is empty and Un closure is contained in Un minus 1 and diameter of Un less than 1 by n. By the above lemma, we can say that intersection of Un is non-empty, as closure of Un is a collection of closed sets which are nested and diameter of Un less than 1 by n. So, to complete the proof, if x is a point of intersection of Un, then x is in U naught because U1 closure is contained in U naught, and as for each n, x does not belongs to An because Un closure is disjoint from An. This completes the proof of the fact that every complete metric space is Baire space. So, in this module, first we have introduced the notion of pair spaces, and then we have proved that every compact topological space is Baire spaces. Also, we have proved that every topological spaces which are complete metrizable spaces are Baire spaces. That is, we have proved that a large collection of topological spaces are Baire. Next, we shall prove that much more topological spaces are Baire spaces. We already know that most of the topological spaces are locally compact. So, if we can prove that locally compact topological spaces are also Baire spaces, then it is possible to say that there are so many Baire spaces. So, let us go to slide presentation to prove that locally compact topological spaces are Baire spaces. So, next we are going to prove that locally compact Hausdorff spaces are Baire space. To prove this, we shall use that open set formation of Baire space. Let Vn be a collection of dense open subsets of a Baire space X. We want to show that intersection of Vn is also dense in capital X. For this, let us choose a non-empty open set U in capital X. We have to prove that U intersection of Vn is non-empty. Since V1 is dense in capital X, we have that U intersection V1 is non-empty. That means we can choose a point, say X in U intersection V1. Now, by applying local compactness, there exists an open set W1 in capital X whose closure is compact such that X belongs to W1 is contained in closure of W1 is contained in U intersection V1 where closure of W1 is compact. Similarly, there exists a non-empty precompact open set W2 such that closure of W2 is contained in W1 intersection W2 which further is contained in U intersection V1 intersection V2. Thus, continuing by mathematical induction, we obtained a sequence of nested non-empty compact sets. Closure of W1 contains closure of W2, contains closure of Wn and so on, where closure of Wn is contained in U intersection Vn intersection V2 up to intersection Vn. Now, since closure of Wn such that n belongs to n is a collection of compact sets with finite intersection property, their intersection is certainly non-empty. That means we can choose a point x from intersection of closure of Wn which is clearly contained in U intersection of Vn. Hence, we have proved that U intersection of Vn is non-empty. that means intersection of Vn is dense in capital X. So, we have proved that capital every locally compact Hausdorff space is Baire space. Now, we shall prove some hereditary property of Baire space. Theorem: any open subspace Y of a Baire space capital X is a Baire space. To prove this, let An be a countable collection of closed sets of Y with empty interiors in capital Y. We have to prove that union of An has empty interior in Y, where Y is a open subspace of a given Baire space capital X. Let closure of An be the closure of An in capital X, then closure of An intersection Y is equal to An. This set An closure has empty interior in capital X as Y is open. If the union of the sets An contains the non-empty open set W of Y, then the union of the sets closure of An also contains the set W, which is open in capital X because capital Y is open in capital X. But each set capital An bar has non-empty interior in capital X. This contradicts the fact that capital X is a Baire space. Hence, it follows that every open subspace of a Baire space is Baire space. So, in this module, we have discussed about Baire spaces. In fact, the notion Baire spaces have been originated from the notion of complete metric spaces. We know the result that every complete metric space is of second category. That means it cannot be expressed as countable union of nowhere dense sets. This has been generalized in case of topological spaces. In case of topological spaces, we have seen that every compact topological spaces are Baire spaces. We have seen that those topological spaces which are metrizable and the corresponding metric is complete are Baire spaces. We have also seen that local compact topological spaces are Baire spaces. Further, we have seen that any open subspace of Baire spaces is also Baire spaces. Thus, we have seen that there are ample supply of Baire spaces. With this, we end this module.